As we continue our work with stoichiometry problems that look a lot harder than they are, I've got 4 examples laid out here, a bunch of words, and you'll notice not a lot of space because none of these take too much work. I do want to point out that we could go through this whole setup and do everything, but I'd also like to point out if you can read things correctly, you can identify where you are and then make it happen. So, as you may recall from the previous video, there are things we have to abstract from these words, like chemical formulas, and we have to come up with a completed balanced chemical equation. We have to get those molar masses. And now let's look at what we actually need. So we want what mass of each reactant is needed. So our big tip-off right there is this idea that something is needed. And the way we've set up these stoichiometry problems, we know what's needed. The catch is you need to produce 1 ounce of copper metal. So that's important information. You have a product, and that product is copper metal. The good news is the ratios win, all right? We have a theoretical yield, and we're going to get our amounts that we need of the other species, the things that are reactants. So while this looks a little messy, we can take care of it pretty quickly. And I'm just going to say 1 ounce, and I'm going to start out with that 28.35 grams of copper, all right? 28.35 grams of copper. And we need to turn that into moles, so we'll divide by the molar mass, which I threw up there, 63.55. And we end up with, and I'm going to go with blue on this to kind of match that, this is our theoretical yield, and it's 0.446 moles of copper. All right. So we're going to compare the theoretical yield not just to our limiting reactant, because there isn't one, we want to know about both, but to our other reactant as well. We're not asked anything about an amount excess, we're not asked anything about a percent yield. We're going to compare our product to our reactants. Since we're looking at stoichiometrically equal amounts, our limiting reactant is both of them. I don't think that's super obvious off the bat, but you can take that knowledge and run with it. If they're asking for the reactant of each, then they're looking for stoichiometrically equal amounts. Both are limiting, and we can do this as one comparison. The balanced chemical equation has 2 moles of copper for every, and I'll just grab some colors here, 1 mole of zinc. And we know that our zinc had a molar mass of 65.39. Which ends up getting us 14.6, which gives us 14.6 grams of zinc as a required amount to start with. And when we do it for the copper nitrate, we know that there's 2 moles of copper nitrate. It's copper 1 nitrate. And we'll multiply by its molar mass, which is 125.56, and we should end up with then 56.01 grams of copper nitrate. All right, and that's it. Those are the answers we were looking for. We could do more steps and come up with more information if we wanted to, but that is what we need. And I'll just toss the orange in there to indicate it. All right, so a bunch of words. All they're really saying is you've got this much product, how much reactants are needed. So, and you're going from there to there. As we look at this one here, it's talking about burning a gummy bear. There's a bunch of words. You can read them in that tiny little font crammed onto the page as I wrote it. Blah, blah, blah. We have sugar's formula. Burned in air, and that's actually very important words. So we'll mention that in air, because that has some meaning. In air, that has some meaning. Produces carbon dioxide and water, gummy bear. So this is important information here. 1.23 grams of sucrose. And what are we looking for? We're looking for a mass of water will be produced. Okay? So that's all our key stuff there. The point I want to make about that in air, what does it mean if we are burning something in air? You've got excess oxygen. So oxygen's 80% nitrogen, 20% oxygen. Hopefully I said air. Air is 80% nitrogen, 20% oxygen. So as we look at this, we've got more oxygen than we need. So when it says in air, what that means is excess oxygen. And what you don't have to answer is how much excess oxygen, because you don't know. You've got an entire atmosphere full of oxygen. So we're only worried about the sugar, and that's the short of it. We want to get water from sugar, and let's make that happen as quickly and painlessly as possible. We have 1.23 grams of sucrose. We're going to divide by its molar mass, which is 342.34. And this will give us what we have, and in this case, we have 0.00359 moles. Now, if we're looking at our steps here, I don't have two reactants to compare because I know my sucrose is the limiting reactant. I'm not asked for an amount excess, so I can just skip to this. Sucrose versus the product of interest. I don't even have to compare it to both products, right? So we only have this. The oxygen, our other reactant, is excess. So I don't need to compare them. And then I'm going to use my limiting reactant, this sucrose, to find out about one of my products, not both, and that is just the water, because it says mass of water will be produced. All right? We know that for every 1 mole of sucrose, there's going to be 11 moles of water, and I will switch this around a little bit. And that will give us 0.0395 moles of water. And of course, we're not asked for moles, we're asked for a mass, so we'll multiply by the molar mass. And that'll give us 0.712 grams of H2O produced. And that is our answer on that one. Again, could be a huge problem, like we were doing before, and we could still do most of this stuff, but we don't have to, right? If they're not asking for as much, we can practice a little bit and cut some corners, right? In this one, we were given one thing, so that was our limiting reactant, and we skipped right to that reactant versus the one product of interest. All right? This is a kind of interesting reaction. A common first-year chemistry class stoichiometry experiment is burning magnesium metal in a crucible, and you hold the lid ajar so you can control the rate of combustion and all that stuff. Since you're burning it in air, though, air, as we said moments ago, is 80% nitrogen and 20% oxygen, it gets hot enough that you can actually react with some nitrogen, and you get a little bit of magnesium nitride. You can take that magnesium nitride and put some water on it, and you'll get magnesium oxide, which is your goal in that particular experiment, and some ammonia gas. And you can actually check for the release of that ammonia gas by holding some pH paper over the crucible as the water evaporates off. It gives a basic pH. Anyway, bunch of words. I'm not going to bother with most of those. They provide some of our template for our chemical reaction. The numbers are of interest to me. We've got an 81.2% yield, and you may say to yourself, well, what does that apply to? You may recall percent yield applies to all the products because they came from the same places in fixed ratios. So percent yield applies to everything, but the number we're given is 27.3 grams of magnesium oxide. And there's a problem I often see in my own students, and I think it's a legitimate hurdle, which is like, what is this 27.3? And we want to produce this, okay? And that means we want to collect it in lab, and so this is going to have to be an actual yield. And this is very similar to this problem. We're just starting one step back. In this problem, we assumed 100% yield, and we just took our mass that we wanted and turned it into reactant amounts. In this one, we have a percent yield. This is not what we're going to have as a theoretical yield, so we need to do that step first. But it's pretty quick, all right? Looking at our steps here, let's get that percent yield. We know percent yield is supposed to be the actual, right, over the theoretical, times 100. When in doubt, write the equation, use it as a checklist. That's my wisdom for you. In this particular case, we know the percent yield. We know the actual yield, and so we need to solve for the theoretical yield. And I'll try and do that with the color we're working with. Our theoretical yield then is going to be 100 over our percent times the actual. In this case, that's going to be 100 over 81.2 times our actual yield, which is 27.3 grams of MgO. All right, this will get us our theoretical yield, and in this particular case, it looks like 33.62 grams. That is our target theoretically. And we need to do stoichiometry with moles, so there's an additional step we'll need to do here. We're going to take that 33.62 grams. We're going to turn it into moles by dividing by the molar mass. And magnesium oxide is 40.31. Which is going to give us, in this case, 0.834 moles of magnesium oxide, theoretically. And I should have moved this over a little better, but this right here is our theoretical yield based on our actual yield and our percent yield. This is it in grams, this is it in moles. And we need moles because that's what our balanced chemical equation gives us. This little step was the only new thing. The rest of it is identical to this, and we'll start with our 0.834 moles, and that's magnesium oxide. We want to find out about both products, and I've really exhausted my color options here. So the magnesium oxide, we know that for every 3 moles of magnesium oxide, we've got 1 mole of magnesium nitride. And so that's the 0.834 divided by 3, that's 0.278 moles of magnesium nitride. And we would multiply by our molar mass because we're asked for what mass, I guess, what mass of each reactant. So we multiply by the 100.95 grams per mole, and that gives us 28.1 grams of magnesium nitride. Sounds like there's a battle going on upstairs. We just said 28.1 magnesium nitride. So that's how much magnesium nitride we would need to start with. Let's take a look at the water. We know that for every 3 moles of magnesium oxide, there's 3 moles of water. So we end up with 0.834 moles of H2O. We multiply by our molar mass, which is 18.02. And we end up with 15 grams, 15.0. And that answers our question. How much did we need to start with? Again, we started at percent yield, which we turned into a theoretical yield, which we turned into stoichiometrically equal amounts of our reactant. So we're just working backwards in that particular problem. Again, picking out what we can and making use of it. Now this problem looks like a disaster. Like my hand got tired writing all these. I was just making them up. When I was looking at this problem originally, I'd written it down as silver plus strontium chloride, which according to the activity series wouldn't happen. So I said that that's what would happen in reverse, and if we cram some electric current through it, we can do electrolysis and make it go that way. So once again, the reaction spontaneously would go that way, but I'm saying we're starting with this and we're going to cram some electricity through it and make it happen in reverse. That's electrolysis. So we'll say we've got electricity. All right, so we want to know a mass. What mass? That's our goal of silver chloride. And when we know about the silver chloride, it is produced. And then we've got some starting amounts that we're working with here. 605 grams of silver and 605 grams of strontium chloride. So most of these words are meaningless except to maybe extract our chemical equation. Here's our goal, which is a theoretical yield, and here's our starting amounts here. So ignoring these words, right? The words make it look harder, but it actually isn't. All right. We're going to take our 605 grams of silver, and we'll take our 605 grams of strontium chloride, turn them into moles by dividing by molar mass. I've got those numbers there, 107.87 and 158.82 grams per mole. This is important information. I've written this a million times. That's what we have, right? Literally. And our goal is to find out what we need. And in this particular case, the 605 over 107.87 is 5.61 moles of silver, and we have 3.82 moles of strontium chloride. As we look at our stoichiometry, we got sorry, my son just ran down, he was yapping at me. 5.61 moles of silver. After the balanced chemical equation here, there's 2 moles of silver, and I want to know about the strontium chloride, 1 mole SrCl2. For the other one, we know that there's 1 mole of strontium chloride for every 2 moles of silver. We've got 5.61 over 2 gives us 2.80 moles of strontium chloride that I need. Spoiler alert, I have too much. And then we would theoretically need 7.63 moles of silver. And I don't even remotely have enough. So we know our limiting reactant and our excess reactant now. This, 5 versus 7, is our limiting reactant. And this, 3 versus 2, is our excess reactant. We aren't asked about the excess reactant. We could do it, and it would be nice if we calculated a full theoretical yield and added everything up. But in this case, we're only asked for the mass of one product, so I'm not going to mess with any of that. I'm just going to take our limiting reactant, right, and find out about our product. As we carry down the 5.61, we know that for every 2 moles of silver, what I'm interested in is the silver chloride. So 2 moles of silver, 2 moles of silver chloride. There's obviously something important happening upstairs. I don't know if you can hear that. All right. This is going to give us 5.61 moles of AgCl. We'll multiply by our molar mass of the AgCl, which is 143.32 grams per mole, and that gives us 803.8 grams of AgCl, which is our goal, massive silver chloride that will be produced. All right, that is a full piece of paper and 4 examples. The idea, once again, you got a bunch of words, but look at how much shorter these were than what we were doing before, which is finding everything. If you can find everything, you can find anything you need. So the answers you need are somewhere in here in the forward direction or the reverse direction, and you don't always need to do everything after a little practice. That's what we have there.